to welcome to our third webinar in our series of 4. And the idea behind this is to bring all of educators that are working with growers in the Northeast up to a common level of knowledge about resistance management. So I would like to acknowledge Sarah, who is supporting this project. So I did go through a lot of this in the first webinar, but just to real quickly an overview, just in case anyone is new. We're going to have 4 webinars. We're going to have some Moodle support, which Laura will touch on very briefly. The big take-home for this, in addition to gaining the knowledge from the 4 webinars, is that we're going to produce a PowerPoint presentation that you could use as a core that, again, will be universal throughout the Northeast when we make resistance management education outreach to our growers. And that kind of goes through this again, and then to just at the bottom, there's a certificate of completion that we'll be offering. And to get that, you would have to participate in at least 2 webinars, use that module and develop a grower training module and use it actually in some of your education workshops, and participate in our verification process. And this is a big component for SARE. They really like to get a good pulse on what people have learned and any behavioral changes. So that's really going to be simply filling out these pre- and post-webinar surveys. And so we'd be asking you to collect surveys from your grower workshops. So that's really all I'd like to cover today, since I think mostly everybody has heard this shtick before, and so I'll pass it over to Laura to briefly touch on the Moodle, unless you want to do that at the end, just in case we run a little long and Andrei needs to leave.
Do that. We can let Andrei start, and then if people have questions about the Moodle, I would be glad to show them through it, because that really is important. So I move that ball to Andrei, and I'll pull his presentation up. Oops, I can't. You're going to have to click on yourself, Andrei, on the top.
Okay. Well, thank you, and thank you for people who are attending the talk, especially the repeat attendees. I didn't realize I'm developing a fan base in Northeastern pest management circles. So anyway, I'm going to talk about insecticide resistance management. Resistance is a heritable change in the sensitivity of a pest population that is reflected in the repeated failure of a product to achieve the expected level of control when used according to the label recommendation for that pest species. This is a definition put together by Insecticide Resistance Action Committee, which is an industry group dealing with insecticide resistance issues. And this is basically how scientists say that resistance is when the product does not work anymore. I guess. Insecticide resistance is a big problem. You can see here a summary from the arthropod resistance database, which is maintained at the Michigan State. This is actually likely to be underestimation because not every resistance case is entered into the database. And you can see that it has been going on for a while and does not have signs of letting go. The line, which is cumulative species within resistance, is kind of leveling off at about 500. This is basically because all the major pest species have already developed resistance. It does not mean that every single population is resistant to every single chemical, but it does mean that at least one case of resistance has been recorded for that species and entered into the database. Look at the number of cases over the years, they do not drop. So it is a serious problem, just as resistance to other pesticides, fungicides, herbicides, and so on. The thing that I want to make sure is that resistance does not happen just to insecticides. It's easy to get on a high horse and say that, that because of chemical-centered mindset, as soon as we stop using chemicals, resistance problem would disappear. That's not true. Pests will adapt to other control techniques. The reason we hear a lot about insecticide resistance is because insecticides are currently the major way to control insects. If they switch to biological control as main way to control insects, then we start seeing resistance to biological control. They were already some cases reported. This goes to other techniques like crop rotation. There is an example of resistance to crop rotation in northern corn rootworm. And, corn and soybeans are usually rotated on an annual basis. 1 year corn, 1 year soybean. Cordworms feed on corn, they do not feed on soybeans. Otherwise, I guess they would have been called soybean rootworms. So if rootworm lays eggs in corn, then over winter, next year larvae die because they cannot feed on soybean. However, rootworm populations develop ability to stay in diapause for 2 or more years. So in this table, for example, only half of them, half of eggs hatch the following season for this population. The rest of them would hatch either after 2 years in diapause, which when corn would come back in a normal rotation sequence, or longer. So this is a rotation-resistant rootworm. So the key is not getting rid of chemical control. The key is integrating different control techniques, and I will talk about that later in my presentation. So who is at risk of insecticide resistance? Pretty much everybody who use chemicals, but not to the same extent. And, if you look at practices, things like repeated applications of the same insecticide as opposed to alternating application of different insecticides, regular calendar-based spraying as opposed to spraying based on an economic threshold, continuous crop as opposed to annual crop rotation, and treatment of the whole field as opposed to spot and perimeter treatments would increase risks. So basically, the more chemical you use, the higher is the risk that it will fail. And that's a typical evolutionary process. Ideally, you have all susceptible insects. However, some factors which are usually unknown and probably random, although there is an argument that pesticides may cause mutations themselves, but at this point there is little evidence actually of that happening. It's possible, but again, we don't know that it is happening. Anyway, so for one reason or another, there would be a few resistant mutants. Normally, they don't do very well, but once pesticide is being applied, these are the only ones that's left. At this point, it's not a problem yet. You don't know that you have resistance because a few of them and they're far between. However, they do not remain few and far between for a long time. And populations build up usually fairly quickly until you see failure. There are several types of cross-resistance, resistance. And there is a resistance to compound, which is the most common one. But there's also cross-resistance. This is when selection by one pesticide would lead to resistance to that pesticide, but also to other pesticides as well. Usually we check chemically similar. Their molecules are similar in structure to the one that was searching for resistance. But it's not always the case. But the case that use one insecticide, but the result end up with resistance to a number of different insecticides. And there is also multiple resistance, which is basically the same end result, but a different mechanism. And this is when simultaneous or subsequent selection by different chemicals results in a population that's resistant to all the chemicals. So again, different result, different process, the same outcome. The so-called superbugs were resistant to a number of different chemicals. So this is something from my research. Colorado potato beetle resistant to neonicotinoids. So imidacloprid, thiamethoxam, different chemicals, same results. Severe defoliation when it should not have been happening. And this is the same in a graphic form. So resistance to imidacloprid increases, and you can see that resistance to thiamethoxam increases with it. When population has never been exposed to thiamethoxam before, we still see the same pattern. Resistance to one increases with resistance to another. So why do we have those problems with resistance? Several reasons. One is pre-adaptation in pest populations. In fact, herbivores have been feeding on plants. Plants have been defending themselves by producing toxins in foliage for billions of years. So many pests already have this, propensity to develop resistance, and sometimes a single small change due to some mutation is sufficient to fine-tune this mechanism up to man-made chemicals. High fecundity and short generation time in pest populations. And this has several implications. One is that once we have resistant mutants surviving, it does not take them too long to build up in numbers. Another thing, because pest populations are high to begin with, the probability that there will be a mutation is higher. It's like buying lottery tickets. If you buy 3 lottery tickets, you buy nothing. If you buy some tickets, you win, $6 gift certificate to your favorite Walmart. So you can in the hole either way, but probability of winning something will be higher if you buy more. The same is with insects. Probability that there will be mutation in trillion of organisms is higher than probability of mutation in 10 organisms or 1,000 organisms. And then finally, selection pressure is usually high because insecticides are applied to kill. That's what they do. So only the resistant ones. Okay. So the first 3 are intrinsic properties of pest populations, of pest species. We cannot do much about them. Selection pressure, however, is under human control. So this is where management can come into play. Before we manage something, it would be nice to understand what's going on and what we are managing. So, what do we know about resistance? So, resistance is a matter of frequency of resistant individuals in the population. Okay, this is not really a problem. Okay, because density is not high enough to cause economically significant damage, and there are few resistant genotypes. So this is a problem, but it is a manageable problem. You spray and problem goes away. and is a big problem because most of individuals are resistant and you cannot control them. Example I use is that, most of us had to manage some kind of crew of people that, once in a while. What the first thing you learn as a manager is that there are people out there who are, let's say, not very smart and diligent, which is okay. With proper management, you can still have work done and you can make best of them because they may have some other talents. However, if you have a crew that consists exclusively of morons, you cannot do anything, and this is when you're in trouble. This goes with the resistance. It's okay to have a little bit, but you don't want to have all of them resistance. This is when problems begin. We know about resistance. In the absence of insecticides, fitness of resistant individuals is usually low compared to susceptible individuals. Okay. Another example I use is that nerds have been around in human population since the dawn of times. Usually they did not do very well because that kind of psychotype is not very conducive to things like hunting mammoths or fighting in hordes of nomads on a horseback. The situation has changed dramatically within the last 20 years, right? So how do you call somebody who called nerd at high school? You call that person boss, because kind of psychotype is highly adaptive to the environment of industrial revolution, and they make 6-7-figure salaries by doing what they're good at. Situation, the environment changes because of insect application. So what used to be a disadvantage becomes an advantage. It comes at a cost. This is the Colorado potato beetle example. I use it a lot because this is what I work with a lot. It's not that I don't know about any other species, but it's convenient because I have slides together. So resistant beetles compared to susceptible beetles, there is lower mating ability of males. Females lay fewer eggs. Overwintering survivorship is much lower, and so on. So in the absence of pesticide selection, they're not doing well. A more serious example is sickle cell anemia in human population. And this is when red blood cells are kind of twisted and do not carry oxygen very well. So people who have it, they start grasping for air after even relatively minor physical exercise. It's manageable, but it is a genetic disease. However, in the environments where malaria is endemic, such as parts of Africa, for example, it is actually adaptive because malarian parasites can't live in those erythrocytes. So we have grasping for air versus having, potentially lethal chill causing liver-damaging disease. But descendants of people from those areas who immigrated, say, to the U.S., they inherit this condition, and they have to manage it as a disease. The same because the environment changed. The same with insecticides. In presence of insecticide, it is an advantage. Those genes, despite of fitness. In the absence of insecticides, it's a liability. What else do we know about resistance? Resistant alleles are usually incompletely dominant, which means progeny of susceptible and resistant parents are somewhere in between in level of resistance. So the hybrids are in between their parents, which I guess makes sense. Another thing that's usually true about resistance is that it's inherited autosomally, which means genes are not located on the sex chromosome, and which means that they follow more or less Mendelian inheritance. Okay, so this is an example with a single gene. Inheritance, what it means when two susceptible parents mate, all progeny susceptible. Two resistant parents mate, all progeny resistant. If resistant mates with susceptible, progeny is intermediate, the so-called heterozygous hybrids, which in between parents for resistance. And if one of those if the homologous resistant but partially resistant mate with each other, then at least part of the offspring is highly resistant. And that's the one that cannot be controlled with pesticide applications. So the task of resistance management is to make sure that this does not happen, that enough susceptible organisms to mate with resistance. So they prevent those guys meeting each other and mating with each other. So what do we do? What can we do about resistance? Okay. So the most important thing is not relying on insecticides alone. They be integrated with other pest management techniques. So, just example again from Coryptator beetle, effect of cooperation of densities of wintered beetles. You can see that simple rotation of the crops results in dramatic reduction in pest populations. This is some of my research survey of commercial grower fields, and you can see that rotated fields had to receive basically twice as many insecticide applications as rotated fields to keep pests under damaging conditions. So, this is an effective way to reduce selection pressure, and adapting to both insects and say crop rotation is more difficult. It's likely to require totally different adaptations, totally different mechanisms, totally different genes involved, and so on. So it's much more likely that a mutation that causes resistance to one chemical would cause resistance to another chemical. That mutation that causes resistance to one chemical would also cause resistance, say, to parasitic wasp or disease or whatnot. For mathematically inclined, probability would be a decimal which is less than 1, right? Probability 1 means complete certainty. As you multiply the abilities, probability of adaptation to chemical, probability of adaptation to, window screen, and probability of adaptation to a parasitic fungus, then, the more those are there, the smaller your product becomes. My son is studying fractions right now, so I was helping him doing homework, and example suddenly occurred to me. So IP, it's not just, way to save the environment. It's also the way to increase sustainability of your chemical control. It will last longer if you have those practices. Okay. If other control techniques are impossible or possible but do not provide sufficient control, then chemically different insecticides should be used. Innovation as a mix. In biology, it's kind of chicken and an egg story where the rotations are better than mixes. Both are being used. As I'm concerned, rotations are better because when you form chemical with another, you relax selection by this chemical. If you move them together, then you are potentially selecting for multiple resistance. Only the types that have resistance to both will survive. And other considerations is that your pest may already be resistant to one of the chemicals in the mix. So while you think you're using a mix, you're effectively using just one chemical and will not notice it because for a while it will provide control. But in fact, by using single compound over and over again, you will end up quickly selecting for a genotype that's resistant for that chemical as well. Yet another consideration is that in mixes, residual activity of different components is likely to be different. So again, in a week or so, you may not have much of a mix anymore. You will have a single residual left. Again, seemingly it works, but in fact, it's already selecting for resistance to mode of action. Having said that, it doesn't mean that mixes should not be used. For what they can be used to expand, to broaden the spectrum of pests which are controlled. One component in the mix can control caterpillars, another go together they control caterpillars and grubs. And it's also better than a single compound because you do have this synergy between them. And mixes can be available as pre-formulated products. For transgenic Bt plants, they have pyramided toxins, more than one Bt toxin active against the same pest expressed in the same plant. And growers can also mix their own. But to me, rotations are better and somewhat different from fungicides, where mixes are much more common. So, what the chemistries are? Chemistries have been classified into different classes, into different modes of action by the Insecticide Resistance Action Committee, which I already mentioned, and which is basically populated by a representative of major pesticide companies. And depending on mode of action, depending on how those insecticides kill their targets, they're placed into one group or another. For example, Group 11, microbial disruptors of insect midgut membranes, which are Bt toxins, in the group their own. Interfere with synthesis of cuticle and insect exoskeleton are built to several groups. 15, 16, and 17 inhibit chitin biosynthesis. For molting and metamorphosis interference, you have groups 18, which is ecdysone agonists and disruptor. Ecdysone is one of the insect hormones. And group 7, which is hormone mimics, which is another hormone. So those are different groups. They have different targets. They're chemically different, but they have the same target. But chemicals in group 18 are similar to each other, and they should not be rotated. Okay, so most, if not all, labels right now have this group on them. So this is Meyer. Active ingredient is imidacloprid, group 4A, right on the front page of the label. Okay. Imidacloprid, same active ingredient, same group. Active ingredient, by the way, could be different. Instead of imidacloprid, it could be thiamethoxam or clothianidine or something like that. But group would be the same, which means while chemical is different, it's structurally similar and it has the same mode of action. It kills in the same way. So they should not be rotated with each other. As an example of a mix, leverage, a mixture of the same imidacloprid, which is group 4A insecticide, and cyfluthrin, which is group 3 insecticide, the pyrethroid. So, since group 4A is here, this would also not be included into the rotation sequence or a mix. Despite group 3 present, the group 4A, so group and it should not be followed by leverage. When several chemicals are used also, and if you for some reason have to use the same chemical, it's important that they are not being applied on generations within the same season, because it enhances selection. For example, you have 3 different modes of action which you target against larvae, but they also affect adults just because there is, adults are still already around when larvae are still around, overlapping generations. Okay, so different chemical classes. It's red, cyan, and guess you call it magenta. Or colorblind people, it's shade of gray, medium shade, light shade of gray, and medium shade of gray. So this is a good rotation sequence. You can see no subsequent generations are being hit by the same product. If you need to spray this one twice for whatever reason, then do it one after another as a block, and that was already discussed for fungicides, because this functionally acts as a single application. Something like that is bad, because you are hitting adults which are children of those adults. So it went through selection by this pesticide once, and then they go through selection for this time. And those that survive this selection probably already have those resistant genes. So this would be additional selection for the same resistant genes. This is not a good approach. So will insecticide rotation always work? No, not necessarily. And again, as far as I'm concerned, it's inferior to integrating chemical and non-chemical techniques. So with chemicals, some resistant mechanisms may work well against totally unrelated compounds from different chemical groups, different targets, whatever, but they digested, say, by the same enzyme. And prior exposure to another group of chemicals may predispose given population to rapid reversion to resistance once this group is used again. So it's not guaranteed that it would last. However, rotation is the best available option for chemical control practitioners. Another important thing is you need to use full label rate of insecticides to whack pest population real well. And sometimes it feels counterintuitive because how come if I cut the rate, I reduce the amount of chemical in the environment, I save the nature, I save money, and I think that I reduce selection pressure for resistance as well. Unfortunately, that's not true. Because, you may have those resistant mutants, right? But more likely you will have fewer of any homozygotes, completely resistant ones. Because there are few of them and there is fitness disadvantage. So chances are most of resistant genes would be heterozygous, which means one parent was resistant and one not. So what gene, for instance, say the resistance gene is from mother, is by susceptible gene father. So those are heterozygotes which should be killed by full label rate. Because resistance is usually incompletely dominant, and those hybrids would be susceptible to full dose because they're not as resistant as completely resistant insects. Not as susceptible as completely susceptible ones, but they're susceptible enough to be killed by the label rate. However, if you cut the rate, there are high chances that they survive. Okay, not a problem at this point. You think that you are a genius because you are saving money and the environment simultaneously by cutting the rate. It seems to be working. However, remember, those heterozygotes mate with each other, a quarter of the progeny will be highly resistant. So, even with this, a knee-jerk reaction usually is to up the dose at this point, because low dose doesn't work anymore. You are not as much of a genius as you gave yourself a credit while it was working. But is that, all you do is wipe out those heterozygotes. You end up with resistant homozygotes and a high resistant population in the end. So, again, cutting rate is a bad idea. Don't do it. Use full label rate. Otherwise, you will pay for it in the future over again. Then the approach is trying not to corner pests, so to say. I talked about reducing selection pressure, and every single bug out there with the sprayer does not make sense because low densities below economic threshold are damaging. You spend more money on trying to kill them all than you are saving by killing them all. And with that also, you make sure that you kill every single susceptible organism. So the only ones that are left after your sprayer chase are resistant ones. Okay? So remember, where susceptible ones mate with each other or with the resistant, where the homozygotes or heterozygotes is completely resistant and will be killed by the high label rate. So by maintaining some untreated population, you add progeny that can be controlled with insecticides, right? So you need to have movement between this refuge, untreated refuge, and the main crop, but as a result of maintaining this population and movement and maintaining the so-called gene flow, you can control your problem for a while. And for protected Bt transgenic crops, it's actually a legal requirement to grow refuge. It's been relaxed lately, unfortunately, which I think was also not a good idea. But, at least it's a requirement. Insecticides, it's not a requirement, but it's a good management practice. And also, if you suspect a problem, if you sprayed something and it doesn't seem to work, then let cooperative extension know, let whoever works with you, your crop consultant, somebody from your state Department of Agriculture. Chances are that something else went wrong. Maybe there was spray malfunction or some product mix-up or whatnot. It's no resistance. But if it is a resistance, it needs to be confirmed, and there are relatively simple ways to do it in the lab. So if resistance is indeed occurring, then it's a whole other thing, and you need to change your management practices so you do not make the situation worse and you don't waste product spraying it on the bugs which are not really susceptible to it. So having lines of communication with the experts open is a good idea. So this is largely everything that I had to say. A couple of shameless plugins in the end. This is a book that I co-edited, so it must be great, right? And it focuses on potato, but there is a chapter that we put on pest adaptation, evolutionary process in pest populations, and that applies to any and even non-crop system. So it could be useful reading. Yet alone I get some tiny puny royalties if you actually buy the book. And then the website that I maintain, again, focus on potato beetle, but it has a section on insecticide resistance sponsored by the EPA. And again, information that's contained over there is applicable to systems other than Colorado potato beetle. So visit it, and it's basically kind of a version of my today's presentation that you can find over there. So, well, thank you very much for your attention. Again, I'm honored that there are people who are interested to listen to me, even though it's second thing off the schedule. And if you have any questions, I'll be happy to entertain them right now.
Here's Andrei. Does anyone have a couple of questions, or he has a couple of minutes before he has to move to his next meeting? And if
people could use the chat box.
Yes, the chat box and the forum on the Moodle. So please don't hesitate to do that, folks.
Yeah, we have so few people on. If people wanted to unmute to just a question, I'm sure we could do that as well.
Okay.
Thank you, Andrei.
Oh, wait. We got one. It said, are all resistant insects less adapted?
No, not all of them, but in most cases, resistance is linked to reduced fitness. There are exceptions when fitness is not affected, or even when fitness is actually higher, and the insect strain would be resistant not necessarily because it's resistant to this chemical, but because its vigor is so great in general that it can withstand chemical application or plant. I believe it's more common in fungi, that kind of situation, rare in insects. So the assumption to make is that there is probably reduction in fitness.
We're going to do a little something on the Moodle, right?
Show people there. I don't think, Claudia hasn't gotten on the Moodle yet, and I'm not sure about anybody else, but I could definitely kind of give a little quick introduction to that. So thank you again.
Yeah, and I have to log out now and run to my meeting, but if somebody has any questions, can go on Moodle or email me or something.
Okay.
Well, again, Andrei, really appreciate it.
No, have a good day. Bye.
Okay.
So just for the folks that may not have logged on the Moodle, I really want to encourage you to do this because this is where you're going, this afternoon is our final webinar, so we won't be able to interact through webinar, but we can continue to interact through the Moodle. And so it's really important that people get on, that they take the survey that is located there. We also sent a link out, and Hillary sent a little message about how important it is for this project application to the final webinar this afternoon, and that went out this morning. But here's the Moodle site that I'm sharing with you. It's the CCE Distance Learning Center. What you would do is just log on, and you can create, actually I think I'm already logged on, so I can't do it. But anyway, you just go on, you follow the directions. It's very easy. Once you get logged on, you will go to the Resistance Management Education course, and that's located through the Ag courses. And, or actually, I think it's the CCE instructors courses. Then you will see a Moodle like this. This is what you're going to be looking at. And we have a forum which just tells people about things. There's an opportunity to introduce yourself. But more importantly, the third thing on the list is the pre-course survey, and maybe I'll figure out how to make that jump out at people a little bit more. Then there's some results from proposal survey. I think full result one needs to be moved down to the webinar one, but let me check that. And each webinar has some of the streaming and download links, the PowerPoints, additional resources may be located there. Have some other links to the IRAC courses, and this is Rich Banaus. He's going to be talking this afternoon. So there's a lot of URL links and links to fact sheets. We've had a few people provide us with other resources, which is exactly what we want to do. I'm going to put a forum under each one of these, so if you have specific questions about fungicide resistance management, insecticide resistance management, or herbicide resistance management, you can add that way. So hopefully people will in there, and that will be open for a very long time, as long as this project really, it can stay there as your resource while you're participating in the outreach portion of the project. Do you have anything else you want to talk about, or do you have any questions?
I don't really have anything else. So everybody here will be able to come to the herbicide webinar at 2:30 this afternoon. I think that'll be really great.
Yeah, for logging on. I'm glad we had the opportunity to. I'm glad that I was able to do that. So see you this afternoon, hopefully.
And
we'll stay on. Yep.
Okay.